Now, I will introduce our group members. We are all from RAS 2131B. I am Nur Naila and my other group members are Nurin Daniel Farisa and Muhammad Haziq Muazzam. Now, I will explain about the introductions of the filters. Audio systems are widely used in everyday devices such as smartphone, televisions, headphones and others. To produce clear and high quality sound, this system requires electronic filters that can control the frequencies of the audio signals. Filters also can allow the desired frequencies to pass while reducing or blocking unwanted frequencies and electrical noise, resulting in better sound quality and improved system performance. Among the most commonly used passive filters are the RC, RL and also RLC filters. Each filter has different operating characteristics and it is designed for specific audio applications such as tone control, speakers crossover network and also audio equalizers. These presentations also discuss the working principles, frequency response and real-world applications of RC, RL and RLC filters in modern audio systems. Next, I will explain about what is RC filters. An RC filter is a passive electronic circuit that is made up of resistor and a capacitor. It is one of the most common filters used in analog electronics because it is simple, inexpensive and easy to build. Besides that, the capacitor changes its reactance according to the input signal frequency. This allows the RC filter to control which frequencies pass through the circuits. In RC filters, there are two filters which are low-pass filter, which allow the low-frequency signals to pass and block high-frequency signals. Another one is high-pass filter, which allow high-frequency signals to pass and block low-frequency signals. The cut-off frequency is calculated using formula of 1 over 2 pi RC. Now, I will explain about the RF filters. An RF filter is a passive electronic circuit that made up of resistor and inductor. It is commonly used in audio systems that are required higher power handling, such as speaker and amplifier circuits. Apart from that, the inductor changes its reactance according to the input signal frequencies. As the frequency increases, the inductive reactance also increases, allowing the RF filter to control which frequency pass through the circuit. So, the cutoff frequency is calculated by using R divided by 2 pi. And lastly is RLC filters. An RLC filters is a passive electronic circuit made up of resistor, an inductor and a capacitor. It combines the properties of RC and RL filters, making it more effective for selecting specific frequencies of range. The RLC filters work based on resonance, where the inductive reactance and capacitance are equal. This allows the circuit to accurately pass or block certain frequencies. There are 4 types of filters in RLC filters. First are low-pass filter that allow low-frequency signals to pass. Second are high-pass filter that allow high-frequency signals to pass. Third, band-pass filter that allow only a selected range of frequencies to pass. Lastly, band-stop notch filter, which block a specific range of frequencies.
So now, I will explain the theoretical concept of passive filter in audio system. Human hearing cover a wide range from 20 Hz to 20 kHz because a single speaker driver cannot handle this whole spectrum safely or accurately. We use passive crossover made of resistor, capacitors, and inductors. Operating without external power, this network route the correct frequency band to the right drivers, protecting the speakers and ensuring clean audio output. Moving to component theory, filters rely on frequency-dependent reactance. Capacitor store energy electrostatically as frequency increase. Their reactance drop, allowing high-frequency travel to pass while blocking low-frequency bus. Inductors store energy electromagnetically. Their reactance increase with frequency, raising low frequency bus while shocking off high travel. By combining these components into RC, RL, or RLC circuits, we can design efficient low pass, high pass, and band pass network for loudspeaker.
On this slide, I will explain how RC filters operate. RC filters use a resistor and a capacitor to control different frequencies. The RC low pass filter, shown on the left, allows low frequency signal to pass while blocking high frequency signals. This is because the capacitor sends high frequency signals to ground, so only low frequencies reach the output. The RC high pass filter, shown on the right, works in the opposite way. It allows high frequency signal to pass while blocking low frequency signals. At low frequencies, the capacitor prevents the signal from passing, while at high frequencies, it allows the signal to reach the output. In audio system, low pass filters are commonly used for woofers and bass enhancements, while high pass filters are used for tweeters and to remove unwanted low frequency noise. Next slide we explain about RL filters, which use a resistor and an inductor. An important property of an inductor is that its reactance increase as frequencies increase. For the RL low pass filter, low frequency signals pass through easily because the inductor has low reactance. As the frequency increase, the inductor blocks more of the signal, so high frequencies are reduced. For the RL high pass filter, low frequency signals are direct to ground through the inductor, while high frequency signals are allowed to reach the output. Like RC filters, RF filters are used to separate frequencies. The main difference is that they use an inductor instead of a capacitor. For RLC filters explanations, which combines three components, a resistor R, an inductor L, and a capacitor C. Compared to RC and RL, RLC filters provides more accurate frequency selections. The circuit works based on resonance. At the resonant frequencies, the inductive reactance XL is equal to the capacitive reactance XC. When this happens, the desired frequencies pass through the circuit while other frequencies are reduced or attenuated. The resonant frequency is calculated using the formula shown on the slide, where it depends on the value of the inductor and the capacitor. Because of these precise frequencies selections, RLC filters are commonly used in audio equalizer and a speaker crossover network to improve sound quality and ensure each speaker receives the correct frequencies range. And then, for audio system applications, the amplifier sends a signal containing many frequencies, and the filter divides them so each speaker receives the correct frequencies range. The low pass filter sends low frequencies, around 20 to 215 Hz, to the woofer for bass sounds. The band pass filter sends mid frequencies, 215 Hz to 2 kHz for the mid-range speakers. The high pass filter sends high frequencies, 2 kHz to 20 kHz to the tweeter for treble sounds. Using these filters produce clearer sounds, reduce distortions, and protects the speaker by ensuring each speaker only handles the frequencies it is designed for.
Now, I will explain about the real-world applications of each filters. Firstly, RC filters which use in tone control circuit to adjust bass and treble. It is found in audio equalizers for frequency adjustment. Commonly found in smartphone, Bluetooth speakers and televisions. Secondly, RF filters which use in speaker crossover network to direct low frequency signals to woofers. It reduces the electromagnetic interference in audio circuits. It is also commonly found in home theater system and professional loudspeakers. Lastly is RLC filters, which used in graphic equalizers for precise frequency control. It separates audio frequencies in speaker crossover network, and it is commonly used in audio mixers and recording studio equipment.
Let's analyze the behavior of a first-order RC low-pass filter. Looking at its transfer function and cut-off frequency formula, the circuit operates in three distinct zones. In the pass band, where frequencies are well below the cut-off point. The capacitor acts as an open circuit because its reactance is incredible high, letting low-frequency bus pass through untouched. At the exact cut-off frequency, the resistor value match the capacitor reactance, causing the audio power to drop by half or minus 3 decibel, while introducing a minus 45 degree phase shift. Finally, in the stop band at high frequency, the capacitor's reactance drop to near zero, shorting the treble signals to ground at a constant roll of rate of minus 6 decibel per octave. Moving on the second order RLC band pass filter, this circuit relies heavily on electrical resonance to isolate a specific band of sound. Below the resonant frequency, the capacitor dominates and blocks the signal, while above resonant, the inductor dominates and shocks off high frequency due to back EMF. However, at the exact resonant frequency, the capacitive and inductive reactance completely cancel each other out. This drops the circuit totally impedance to its minimum resistive value, allowing maximum current and full audio power to pass through the speaker with zero phase shift. By combining both reactive elements, we achieve a step roll of slope of plus minus 12 decibel per octave, making it highly effective for dedicated mid-range audio routing.
For conclusion, RC, RL and RLC filter are essential in audio system because they improve sound quality by controlling different frequencies range. Each filter has its own function and applications depending on the system requirements. Overall, these filters reduce noise, minimize distortions, and ensure that each speakers reproduce the correct frequencies for better audio performance.